I'm going to tell you about some joint work that I did with Caleb Eckhardt and David Pask, whom some of you may know, and also with three people that I don't think you've met, Kit Fieldhouse, Daniel Gent, and Ian Gonzales, who are students from the University of Montana, or were, they just graduated. And what I'm going to tell you about is some work that we did last summer on moves or transformations on higher rank graphs that preserve the Morita equivalence of the associated C-star algebras. Before I get started, though, I want to follow Brad's lead and acknowledge that the University of Montana is in the Aboriginal territories of the Salish and Kalispel people, and I want to honor the path that they have always shown us in caring for this place for the generations to come, and acknowledge and honor the history of the indigenous peoples who have called Montana home. Past, present, future. And so having recognized some of the history of this place that I'm in, I'm currently in my office. Let me tell you a little bit about the history of the math that I want to talk about. We've heard some fairly different flavors of classification of operator algebras in different ways in different talks. And the sort of classification that inspired this work of ours on moves on higher rank graphs, for me, the sort of touchstone moment is this 2016 paper by Søren Eilers, Gunnar Restorff, Efren Ruiz, and Adam Sorensen, where they proved that two directed graph C-star algebras, C-star E and C-star F, are stably equivalent if and stably isomorphic, bara Morita equivalence, if and only if one can get from the graph E to the graph F by a finite sequence of one of these 6 moves and their inverses. So we have S is deleting a regular source, O is for outsplitting, I is insplitting, R is reduction, C is the Kuntz splice, and P is the butterfly move. So this work, in addition to building on earlier work of all of the authors, it also drew on a lot of work by Teresa Bates and David Pask, Doug Drinan, in particular the work in his thesis, and Tyrone Crisp and Daniel Gao. This is what I get when I start saying full names of people. So these authors were doing earlier work on moves on graph algebras, operations you can do to a graph that don't change the resulting C-star algebra very much. Rotem's work on classification of Kuntz-Krieger algebras led to the Kuntz splice move. And the final proof that these 6 moves are all you need really drew heavily also on work of Boyle and Huang from dynamical systems. So this gives us a classification up to stable isomorphism of graph C-star algebras, unital graph C-star algebras, so where the graph has only finitely many vertices, but we're allowed to have infinitely many edges. Eilers, Restorff, Ruiz, and Sorensen in the same paper actually also obtained a classification up to isomorphism of these unital graph C-star algebras using ordered filtered K-theory. And more recently, Søren Eilers and Efren Ruiz, and in conjunction with Sarah Arklint, have work on sort of a geometric classification of these graph C-star algebras. So a classification in terms of moves or operations at the level of the graph, not at the level of the C-star algebra, much less at the level of the K-theory. And so they've proved that 2 unital graph C-star algebras are isomorphic if and only if you can get from one to the other by doing outsplitting. It's the same outsplitting move that was mentioned on the previous slide. In a variation on insplitting, this I plus, and then variations also on reduction, Kuntz splice, and the butterfly move. The one that's missing here is removing a regular source. Anytime you do that, you're definitely not going to preserve isomorphism. You end up with a different matrix algebra, essentially. And so Not that all graph algebras are matrix algebras, but you end up with a different degree of matrices involved. And so that one couldn't show up if you're looking for isomorphism. So that's what's known at the moment, or at least known to me, about classification, in particular geometric classification of graph C-star algebras associated to a graph with finitely many vertices. And this work that my students and I and Caleb and David did last summer it is a first step in extending these classification results for higher rank graphs. So we do not yet have classification results, but that's sort of the eventual end goal. One might notice that it took, depending when you start counting, it took more than 10 years, maybe even more than 20 years to get from the initial work on the moves on graph algebras to a classification theorem. And so we are still in year 1 or 2 of classification results for K-graph algebras. But what we have done so far, and what I'm going to tell you about, is we've found 3 moves we can do on K-graphs, 3 ways to change a K-graph in a way that will preserve the Morita equivalence class of its associated C-star algebra. The first one is deleting a sinc, which is the analog of move S, so removing a regular source for graph algebras. And the reason is that the Kunz-Krieger conventions, the definition of the algebras for Eilers-Restorff-Rees-Sorensen, they treat the source projections the same way that we treat the range projections. And so a source for them becomes a sinc for us. And that may, if that was nonsense, maybe it'll become more clear in a couple slides. And if not, no need. It's our analog of their move S, and it happens to also start with an S, so lucky us. Then we also have a move Insplitting, which Eilers-Restorff-Rees-Sorensen also had a move Insplitting, but again, because of this sort of reversing sources and ranges, it really should be thought of as the analog of their outsplitting. And again, just as with outsplitting, for directed graphs, insplitting for K-graphs, for higher rank graphs, gives us an isomorphism of the associated C-star algebras. And delay. Now that one wasn't on the list. It was, however, one of the moves that was considered in some of the early work by Doug Drinan and Bates and Pask, and it's related to flow equivalence for shifts of finite type. It's sort of an inverse to reduction, and it turned out for us to be more tractable, and I think somehow it feels to me more elegant than reduction in the K-graph case, but I will let you judge that once I get there. Okay. So now I have thrown a whole bunch of words at you, and I suppose I should start defining some of those. So I want to start by telling you what a K-graph is, and then I'll tell you what a K-graph C-star algebra is, and then I'll tell you about what exactly these moves are, and a quick sketch of some of the proofs of how we proved that these 3 moves, sinc, deletion, insplitting, and delay, don't actually change the Morita equivalence class of your C-star algebra. So higher rank graphs, or K-graphs, were introduced by Alex Kumjian and David Pask, building on earlier work of Robertson and Steger. They're a generalization of directed graphs, and the way that what follows is not Alex and David's definition. So apologies, Alex and David, if you're listening. But for me, this was the approach that worked for us last summer, and it's an equivalent way to describe K-graphs. So the way that we're going to think about a K-graph is we start with a directed graph, and we color the edges using K different colors. That K in the number of colors should be the same K. It's telling us the dimension, essentially, of our higher rank graph. And it's not enough to just throw the colors on. You also need to have you need to specify a factorization rule or an equivalence relation on the paths in this K-graph. So anytime you've got two different colors, red and blue, for example, and you've got a path from V to W that consists of a blue edge followed by a red edge, then the factorization rule pairs it up with exactly one red edge followed by a blue edge from V to W. These intermediate vertices can be the same, they don't have to be, but we require that the source and the range, the W and the V, stay the same. However, that's not even quite enough. Not every equivalence relation like this, not every factorization rule is going to give us a K-graph. And the thing is that, as I said, a K-graph is supposed to be a K-dimensional generalization of a directed graph, in the sense that in a regular directed graph, which I sometimes call a one graph, paths are one-dimensional, right? They're just edges. So in a K-graph, we want the paths to be sort of K-dimensional hyperrectangles. And so in order for, and you can perhaps see this a bit if we go back to that previous slide with this picture of the path from V to W, that, you know, a path from V to W really means a square, an equivalence class of paths from V to W. So in order to be a K-graph, in order for this edge-colored directed graph with a factorization rule to actually give us a K-graph, we need to know that the factorization rule is going to build us out a well-defined cube anytime you start with a three-color path. And the magic, and this is from this paper by Hazelwood, Rayburn, Sims, and Webster, is that all you have to do is check cubes. Even if you've got 17 or 23 or a million different colors that you're looking at, all you need to do is check that paths involving three edges of three different colors build out nicely to give you a three cube. It's essentially associativity. Once you know that 3 dimensions works, then you want to check that 4 dimensions works, and there's enough overlap between the sort of component 3 cubes in a 4 cube that everything is forced to work. So let me say a little bit in pictures what I mean. Suppose we start with a 3-color path, black, red, blue, and red. And I've tried to draw these pictures so that it looks like it's lying along a cube. It looks 3-dimensional. So if we have a factorization rule, then this black-blue path from the top corner down to the forward corner has to be equivalent to a blue-black path from that top corner down to this forward corner. Well, and now we've got a black-red path. So that has to be equivalent to a red-black path from that back corner to the front corner. And now we've got a blue-red path, and so that has to be equivalent to a red-blue path from that back corner over to the bottom left corner. So let's pause for a second and think back about our original path, right? The black-blue-red path. What if I started, rather than by rewriting this black-blue path, by rewriting this blue-red path? That has to become a red-blue path. And now I've got this black-red path here. So if I rewrite that, it becomes a red-black path. And so now as I said, I'm trying to think about all of these as happening on a cube. And so if you sort of try to superimpose this bottom cube picture with this top cube picture, you see that these back two red edges are in the same place. So what we did is we started with that same path, right? That black, blue, red path from the back corner to the front corner. And we started sort of unpacking that in 2 different directions, sort of peeling our orange right and then left. And we got to a place where these 2 different approaches landed on the same point in the cube, namely this back red edge here. So in order for this to be a k-graph, in order for our factorization rule to give us a k-graph, that back red edge has to be the same no matter how we peel the orange, no matter which way we go around the cube. And similarly, again, thinking about these as occurring on a cube, we've got this blue-black path on the top version up there, and it starts and ends at the same point as this black-blue path that we have on the bottom picture of the cube. So in order for our factorization rule, our pairing of two color paths to give us a k-graph, those left-hand paths, the blue-black or black-blue paths, those have to give us the same face. Those have to be equivalent in our factorization. But as I said, the magic of this Hazelwood, Rayburn, Sims, Webster result is that all you have to do is check the three color equivalences. Once you know that all the three color paths factor out nicely, sort of wrap around a cube, give you a well-defined cube, then you know you have a k-graph. So that's a k-graph. It's a directed graph with k different colors of edges and a factorization rule or an identification of blue-red paths with red-blue paths and blue-black paths with black-blue paths, such that any three-color path gives you a well-defined cube. And then once you've got a k-graph, you can build a C-star algebra out of it. So C-star lambda is a universal C-star algebra that's generated by projections for the vertices and partial isometries for the edges in a way that the multiplication of these generators corresponds to concatenating the associated edges in your k-graph. So for example, we require that the vertex projections are mutually orthogonal. If we had a red-blue path, say F is red and E is blue, that's equivalent to a blue-red path, so E prime is blue and F prime is red, then the product of those two generators on the left should be the same as the product of the two generators forming the right-hand part of that square. So the Kunz-Krieger relations force us, include the factorization rule here. We require that the source projection of any edge is the projection at the source of the edge, at the source vertex. And we require that the range projection of any edge is a sub-projection of the projection at the range vertex. More precisely, if you fix a color and you look at all of the edges with a given range and that color, the sum of their range projections is precisely the projection at that range vertex. So C-star lambda is a universal C-star algebra satisfying these relations, and by which I mean that if you've got any other family of projections and partial isometries in some other C-star algebra that satisfies those Kunz-Krieger relations, then we have a surjective star homomorphism from C-star lambda onto the C-star algebra generated by these other projections and partial isometries. And this is a really useful tool for proving the sorts of Morita equivalence results that we're going to be getting later, in particular because of the gauge invariant uniqueness theorem that Kumjian and Pask proved in their first paper on K-graph algebras. And they proved that first, you've always got a natural action of the K-torus on C-star lambda, if lambda is a K-graph. Again, K is supposed to be the same integer here. And the way that works is that the action is going to fix all of the vertex projections. And on the edge partial isometries, it multiplies the partial isometry SE, but if E had color I being between 1 and K, then you just multiply it by the ith element in your K tuple of Z being an element in T to the K. So it's just a rescaling by elements in the K torus. And the gauge invariant uniqueness theorem tells us that essentially anytime you've got a Kunz-Krieger family that has a gauge-like action, that has an action beta that intertwines with this canonical gauge action alpha, then that tells you that this map pi from C star lambda onto the C star algebra generated by this other Kunz-Krieger family is going to be an isomorphism, as long as it's not obviously non-isomorphic, right? By which I mean, as long as all of the vertex projections are mapped to something that's not zero. If you've got a gauge action on the target that intertwines with the classical gauge action, then your map pi here is an isomorphism. As I said, that'll come up in our proofs of the theorems that these three moves preserve the Morita equivalence class of our K-graph C-star algebras. But first, let's just look at an example quickly. So here we've got one vertex, two blue edges, F1 and F2, and a red edge, E. So in order to make this into a K-graph, I have to specify for each red-blue path, for example, EF1, it has to match up with a blue-red path. And I've got some choice there. I could do, as I've specified here, F2 and then E. Yeah, I read my paths right to left throughout this talk and throughout any paper of mine you'll read. So that's sort of necessary in order for the nice thing that I said about the Kunz-Krieger relations, that the projection at the source of an edge is its source projection. For that to match up, I then later need to read paths from right to left. So that's what I do. So I have to make a choice here. I've got a red-blue path, EF1. It has to be equivalent to some blue-red path, and I could pick either F2E or F1E. If I pick F2E, then when I look at the other red-blue path, EF2, that has to be equivalent to F1E. And so the C-star algebra that we get out of this turns out to be O2 cross Z. So the O2 is coming from the copy of F1 and F2, right? We've got only one vertex, so our partial isometries are all actually isometries. And the fourth Kunz-Krieger relation that said that the range projections of the edges with a given color need to sum up to the projection at that vertex gives us the Kunz relation, right? F2, F2 star plus F1, F1 star is going to have to be 1. And the action is coming from the fact that E takes F1, conjugation by E, or conjugation by the partial isometry associated to E, takes F1 to F2 and vice versa. So, and then a bit of notation as well. If we've got a K tuple in n to the K, then I'll write lambda upper n to be the set of equivalence classes in my K graph, which have n sub I edges of color I for each I between 1 and K. And the factorization rule tells us this is well defined, right? When we did our equivalence relation, a blue-red path with one edge of each color, red and blue, was equivalent to another path that also had one edge of each color, red and blue. And lambda 0, well, what's that? Lambda 0 is the set of morphisms that have 0 edges of each color. So that's just the vertices. Okay, so now this is probably a good time to pause for questions, because now I'm going to assume that we're at least conversant with the idea of what a K-graph and its C-star algebra are. I'm going to start telling you about the 3 moves: sync, deletion, insplitting, and delay. Okay, well, I'll keep moving, and if there are more questions, let me know. So a sink for us is just a vertex which emits no edges of color I. So it's a sink for color I. It doesn't have to be a sink for all colors. Let me pop ahead to this example here. So V here is a blue sink, but it's not a red sink. Okay, and if you've got two vertices in your K-graph, then we say that W is less than V, or W, I think of it as W is downstream from V, if there's a path with source V and range W. And so the theorem for sink deletion is that if you have a sink and you delete that vertex V and all of the vertices that are downstream from V, and then all of the edges that sort of come along with this, then you end up with a new K-graph. That's part one of the theorem. And moreover, the new K-graph has a C-star algebra, which is Morita equivalent to the C-star algebra you started with. So back to that example, if we delete V, because it's a blue sink, we're allowed to do that, but then we have to delete all the vertices that are downstream from V. Well, in this case, there's just the one vertex that's downstream from V, but if I delete this vertex, then I also am deleting all of these four edges that are coming into that vertex, and so I get this picture here. And now these end vertices, those are both blue, well, those are all sinks. This one's a red sink, this one's a red sink, and that one's a blue sink. And so we can then delete those, and then we're left with just two singleton vertices, with each with a red and a blue loop at each one. So a single vertex with one red and one blue loop, the C-star algebra of that K-graph is the continuous functions on the two torus. And so this K-graph that we started with, its C-star algebra is then Morita equivalent to the direct sum of two copies of the continuous functions on the two torus, which to me is not obvious if you just look at the picture. Perhaps it is to Alex or David, somebody who's been working with this for decades, but not to me. So that's sink deletion. That's I think the easiest of the three moves to explain. So let's move on and talk about insplitting. So the idea with insplitting is that you're going to take a vertex V, make two copies of it, and then split up the edges that are coming into V among those two vertices. All of the edges that were coming out, you're going to make two copies of those, right? One coming out from V1 and one copy coming out from V2. That in directed graphs, that's all you do. With K-graphs, the factorization rule means that we have to be careful about how we divide up the incoming edges to make sure that the thing we get out at the end is still a K-graph, right? In order to be a K-graph, it's not enough to be just a directed graph with colors. You have to have a factorization rule that behaves nicely, that gives a well-defined 3-cube for any 3-color path. So the way we do that is we have this pairing condition. If you've got two edges with range V, and they both live on the same equivalence square. So here, if I were going to draw a picture associated to this relation, FA1 is equivalent to GA2, I would have, say, F being a vertical edge and G being a horizontal edge with the same range, that range being this vertex V, and then the A1 and the A2 are in back, sort of filling out the square. So anytime that happens, if F and G are in the same factorization square, then we're going to need to put F and G into the same set in our partition, right? We're going to partition the edges that have range V into two non-empty sets, E1 and E2. And then we define our new K-graph, our insplit K-graph, lambda 1, by saying, well, it's going to have the same vertices that we originally had, except now we've got two copies of V. We just import all the edges that don't involve V. The edges in the set EI are going to go to vertex VI. And then we make two copies, E1 and E2, of all the edges that had source V, and the edges E1 are going to have source V1 and edges E2 are going to have source V2. So that tells us what the graph is, and it essentially tells us what the coloring is. Any edge's color is going to just be the color that it had in the original K-graph. But it doesn't tell us what the factorization is. And essentially, what we do is we take the factorization from lambda, from the original K-graph, and import that into lambda I whenever that makes sense. And I think this might be clearer with a picture. But we need this pairing condition so that we can just take the factorization in lambda and import it into our new K-graph, into lambda I. Import it into lambda I in a way that makes lambda I a K-graph. So another interesting thing to note is that here we required these sets E1 and E2 to be non-empty. So that requirement can mean that we actually can't always insplit at a given vertex. So for example, here we've got one vertex and two edges of each color. G and F are blue and A and B are red. And so because we've got multiple edges of each color, we've got some choice in the factorization. If I decide that the blue-red path FA is equivalent to the red-blue path AF, so those edges just commute, and A also commutes with G, then that pairing condition we saw is going to tell us that since A and F are both sort of at the front corners of their square, A and F have to be in the same equivalence set, say they're in E1. But then A and G are also in the same set. And so we're going to have A, F, and G in E1. And I guess I didn't quite tell you enough information here, but okay, so now we need to know, we also need to know what the path, if we look at the path G and then B, so the blue-red path G and then B, well, that's going to be equivalent to some red-blue path. I've already talked about the red-blue paths that started with A and then did something, so it's going to have to be equivalent to a B and then something. So in other words, we have B blah is equal to blah, maybe a different blah, B. But what that means is that B is going to have to be in the same equivalence class as either G or F, something. It actually doesn't end up mattering because we know that A, G, and F are all in one set, E1, so B is going to have to be in E1 also. So E2 is then going to have to be empty, and so we can't insplit at this K-graph if we have that factorization, if we say that A and F commute and A and G commute. On the other hand, if we say that AF equals GA and AG equals GB, then here the sort of front edges in that are A and G and A and G. And so we can take E1 to be the set A and G, and then turns out that, again, no matter what choice you do for the other two blue-red paths that I haven't talked about, we'll be able to take E2 being the set B and F. And so then if we insplit, what's going to happen? This is a bit of a messy example because we've got all these loops at the one vertex. But what happens, so we've got two copies of the vertex V, V1 and V2. And all of these edges, A, B, G, and F, they all had source V, so we're going to make two copies of them. And they're all going to, the copy 1 is going to have source V1, and copy 2 is going to have source V2. And whether its range is V1 or V2 depends on whether it was in the set E1 or the set E2. So the E1 edges are all going to have range V1, So you see that both the A1 and G1 and the A2 G2s have range V1. And the E2 edges, the B and the Fs, are going to all have range V2. And so now we need to figure out what's the factorization. And because we split up the E1 and the E2 in this way, we can basically we want the factorization in the new graph to be essentially the same as it was in the old graph. So F followed by A should be equivalent to A followed by G. And so how does that make sense? So if I do a blue edge, say F2, then I can follow that by A2. So then that has to be equivalent to an A followed by G that goes from V2 to V1. So the only A edge that starts at V2 is A2, and then the only G edge that I can do is G1. So A2 F2 is now equivalent to G1 A1. And similarly, we had A2, if I could also have done F1 and then A2. So that's now a blue-red path from V1 back to itself, and that should be equivalent to some A followed by G from V1 back to itself. Well, the only A I can do to start at V1 is A1, and then I can follow that by G1. So we see that A2 F1 is equivalent to G1 A1, and similarly. So even though we had some choice in how to define the factorization rules for this, this directed colored graph that we started with, once we've insplit, there's really essentially no choice. You just follow your nose and are careful with your indices. And so once you've got, if you are able to insplit at a vertex, doing so does not change the C-star algebra. As long as you started with a K-graph which is row finite and source free, one can look at more general K-graphs. I almost never do. The Kunz-Krieger relations get more messy. There's enough to keep me busy here in the row finite source free world. So that's where I play. And so how do we prove that we don't actually change the C-star algebra we get out in the end? Well, I'm going to define a Kunz-Krieger family for the original graph lambda inside the new, the C-star algebra of the new K-graph. So, and it might be sort of a follow your nose. You take, for any vertex that wasn't the one you split at, I'm just going to define the QW to be the projection at that vertex. And for the one that I split at, I'm going to just add those together. And those are orthogonal projections, so their sum's a projection, and so that's the projection I want for QW. And similarly with the edges, right? We imported a whole bunch of edges and we duplicated the ones with source V. So I'm just going to let my new partial isometry TE associated to the edge E in lambda be the generator SE of C star lambda I if the source of E isn't V, if it's not a problem. And if the source of E was V, so I've got two copies of the edge E in C star lambda I, well, I'll take TE to be the sum of those two. And then you check that these projections QW and partial isometries TE satisfy the Kunz-Krieger conditions for lambda. So they multiply the same way you would compose edges in lambda. And so the universal property of C star lambda tells us that we have a star homomorphism from C star lambda into C star lambda I. And then you can actually show that it's onto, that every single generator of C star lambda I is in the image of this map pi. And you prove that it's injective by using the gauge invariant uniqueness theorem. You notice that we haven't really changed the length of any of the paths in doing this, right? This was an edge, it had color I. This one is an edge with color I. And so this map pi is going to intertwine the two gauge actions, one on C star lambda and one on C star lambda I. And so we actually get an isomorphism here of K-graph C star algebras. So in this one, and I think actually in all of the moves, I think the clever part that my students came up with last summer was finding the right way to write down a move so that after you do it, you still get a K-graph. Once you've written down the move and you've made sure that it's still a K-graph, it's usually fairly obvious, maybe not obvious, but it's fairly immediate to see what the new representation of your old K-graph is, and then you use the gauge invariant uniqueness theorem to tell you that this representation is injective, and then you show that what you get, well, it isn't always an isomorphism, but it's a full corner in the other cases. So, all right, I've got 8 minutes left. Let me tell you quickly about delay. So for a directed graph, the way delay works is you just take an edge and break it into two. You put a vertex in the middle, so you separate E into E1 and E2. With K-graphs, this gets a little bit more messy. So here's how that works. Suppose you want to delay at the edge E. Well, if you've got another edge E prime that's the same color as E, and they're sort of parallel on a factorization square, right? If you were drawing this relation EF equivalent to F prime E prime as a square, you'd have E going down and F going over, and then at the top, E prime going over and F prime going down. So you see that the E and the E prime are opposite each other on the factorization square, and they're the same color. Anytime that happens, then we'll put E prime in our set E script 1. And then we'll look at any other edges that are opposite on a factorization square to E prime or to E, and just wash, rinse, repeat. And then we're going to have to delay at everything in this set E1. So the way that works, if we had, here's a picture, we've got, suppose in this picture I wanted to delay at the edge G. So I would then also have to delay at the edge F. So I'm going to add in two new vertices here, and we've got the edges G1 coming into the new vertex and G2 leaving, and F1 coming into the new vertex and F2 leaving. But now, look, we've got this blue-black path, AF1, that's not equivalent to any black-blue path. So we need to add an edge for each of these rectangles that we've stretched our commuting squares out into. We need to add an edge for each one of those commuting squares. And the color of that new edge is going to be sort of the other color. If we're delaying black edges by splitting the black edges into two, then the new edge, this E alpha that we add, is blue in this case because we were looking at a black-blue factorization square. Again, the challenging part is making sure that doing this is going to result in a structure that's still a K-graph. You have to figure out, well, what should the factorization rule be? So I guess it's maybe evident to see from the way I've drawn this that I want to say AF1 is going to be equivalent to G1 E, the edge for AF. But then you have to check that that does indeed give you a K-graph, that any length 3 colored path is going to give you a well-defined cube. So there's a lot of cases to check, but it does work. And again, it's once you've had the right idea, it's a follow your nose and be careful with the notation. So that's the first part of the theorem that we proved about delay with Caleb and Kit Fieldhouse, Daniel Gent, Ian Gonzales, and David Pask, is that if you start with a row finite source free K-graph, lambda D is also row finite and source free, and its C-star algebra is Morita equivalent to the C-star algebra of the K-graph we started with. So here, again, we define a Kunz-Krieger lambda family inside of C-star lambda D. So we just take the projections to be the same. The projection associated to the vertex V is just going to be the generator for that vertex inside C-star lambda D. And the partial isometry for the edge E, well, if we didn't delay at E, then I'm just going to use the SE again, the same generator in C-star lambda D. And if I did delay at E, then I'm going to take those two new edges that I created and multiply them to get the new partial isometry TE. Okay. So you check that this gives you a Kunz-Krieger lambda family in C-star lambda D. So we've got a star homomorphism then from C-star lambda into C-star lambda D. And we use the gauge invariant uniqueness theorem to tell us that C-star lambda is actually isomorphic to the image of this star homomorphism. And then you've got if you take P to be the sum over all of the vertices in lambda 0, so all of the vertices that weren't new ones we created by delaying, this is a projection in C-star lambda D, then turns out that the corner associated to that projection is actually the C-star algebra generated by this Kunz-Krieger lambda family. And so since this is a full corner inside C-star lambda D, that tells us that C-star lambda and C-star lambda D are Morita equivalent as we wanted. Let's see. I think I will, in my last couple of seconds, I do want to say that Stephen Allen's got some nice results about corners in K-graph algebras, which were very handy for, in particular, proving this result, the final piece of the result about delay. So I think it's not a very well-known paper. I didn't know about it until David Pask pointed it out to me, so I wanted to publicize that work. And I also wanted to mention that another nice thing my students proved last summer is that they gave a fairly general way for constructing actions of the K-torus on a K-graph, because we weren't, to apply the gauge invariant uniqueness theorem here in the delay case, because I sort of stretched out, I used two generators here to correspond to one partial isometry in lambda. I can't use the canonical gauge action on lambda D to intertwine with this projection pi from C-star lambda into C-star lambda D. So we have to come up with a different action, and my students came up with a nice, actually fairly general way to phrase when one can do that, when one can construct sort of a variant on the gauge action, and that was what we ended up needing to use here. All right, so thank you very much for listening, and thanks again to the organizers for inviting me to talk, and thanks to the NSF and the University of Montana for supporting this research.